head on to our next presentation. It comes from Sara Karamati from Georgia Tech, who's on the East Coast here in the United States. So unfortunately, the time zone match didn't really work out to do this live. So she did send a great video presentation. It's investigating DPUs and their performance impact on molecular dynamics applications. So let me set that up really quickly for you all.
Hi everyone. Today I will be talking about how we might use data processing units or DPUs in scientific computing applications on HPC-oriented systems using molecular dynamics as a case study. This is a joint work with Sandia National Lab and Ryan Grant from Queen's University. When we look at a distributed memory cluster, the building block is a compute node. A compute node has a host processor and memory, with a memory hierarchy, such as one or more levels of cache, disk, or other types of storage. The host communicates with other hosts via a NIC, which is a network interface controller or card. And the compute nodes are connected by a network. The idea of a data processing unit or DPU is to extend the computational capabilities of a network interface card by adding a processing unit and memory. However, compared to the host, its computational power is lower. The question is what we can do with such a lightweight processing unit on network interface card. There are many ideas that have been developed or proposed. These include accelerating network applications like packet processing and traffic shaping, improving network storage and sensor algorithms, for example, distributed key-value stores, optimizing runtime systems for everything from resource management to fault tolerance support. And in HPC, people are looking at things like accelerating MPI operations. But the one that has not been explored much is HPC algorithms. In this work, we investigate if we can use the processing power of DPUs to accelerate the HPC applications. But first, let's review some of the related works. Blue's MPI accelerates non-blocking all-to-all operation by overlapping communication by computation. They accelerate three-dimensional fast Fourier transforms by replacing collective MPI operation with Blue MPI's operation, with minimal changes in the code. The second work is Pennant MiniApp acceleration using BlueField DPUs. Pennant is an unstructured mesh physics miniapp. They offload some tasks to BlueField with no fundamental changes to the code base. And they found no appreciable performance improvement over the baseline implementation. Another work is accelerating CPU-based distributed DNN training using BlueField 2 DPUs. They explore offloading independent phases of deep learning training to BlueField, and they can improve the performance of training by up to 15%. In all these works, they relied on middleware porting or symbol offload schemes, with no fundamental changes to the algorithm. Can we do better by restructuring algorithms? Now let me explain what our focus area in this work are. Regarding applications, we are interested in scientific computing workloads. Our focus is on redesigning algorithms and restructuring the code to better fit the DPU. So we will make algorithmic modifications in the target application. And specifically in this work, the application of interest is MiniMD, a molecular dynamics benchmark. Regarding platforms, we use NVIDIA Bluefield 2 data processing unit, which is based on a general-purpose multi-core processor. We use DPUs in off-pass mode. In this mode, the DPU functions as a separated host. In other words, you can consider it as a standalone CPU. By contrast, many prior usage models have assumed on-pass or inline processing. In on-pass mode, as soon as a packet comes into the system, or just before it leaves the system, the network interface card performs some computation directly on that packet before passing it to the host or sending out on the wire. Regarding programming, we use readily available open standards like MPI and OpenMP for programming the DPU, instead of lower-level communication libraries such as OpenSnappy. Now let me explain how MiniMD works. MiniMD calculates the position and velocity of a set of interacting particles in discrete time steps. In the distributed memory setting, the simulation domain is divided spatially among MPI processes. Each process owns its particles, and in each iteration computes force on these particles and then updates the position and velocity of these particles. MiniMD only considers short-range forces. That means each particle interacts only with other particles that are geometrically close. For instance, consider a particle at the center of the highlighted circle. This particle interacts with other particles within the circle with radius RC, which is the cutoff distance. To keep track of all the particles in the enclosing circle, the code stores a neighbor list for each particle. During the simulation, the particles move. So some particles can move out of the circle or come inside. Therefore, these neighbor lists must be updated. But those updates are very expensive. To reduce that cost, every list includes a buffer of extra particles. This buffer lies between two circles shown in this figure. The parameter delta in the figure is a tuning parameter that determines how frequently we need to update the neighbor lists. Now consider a particle in the center of the circle shown in this figure. In order to compute forces on this particle, process 3 needs to know the position of particles in the enclosing circle. As you can see in the figure, some of the particles are assigned to the process 4, Therefore, in each time step, before computing forces on particles, processes communicate the position of particles in ghost zone, white highlighted area in the figure, with neighboring processes. Particles move through subdomains, for example from process 1 to process 2 or vice versa in this figure. So the algorithm reassigns the particles to their new processes as they move through the spatial domain. In this slide on the right, I show a flowchart of MiniMD basic tasks. The tasks are the blue boxes in this figure. For now, the details are not important. Instead, the important part is that each task itself can run in parallel. But the sequence of tasks is serial. That means if we want to offload a task to the DPU, we have to break these dependencies somehow. Here is what the execution timeline looks like. The algorithm iterates over time steps. In each iteration, the computational bottleneck is the force computation, shown here by red FC boxes. After each force computation, MiniMD updates the velocity for each particle. This operation is shown by red UV boxes in this figure. But remember that the particles move. Therefore, we need to frequently update the neighbor lists. The neighbor list update operation is shown as blue MB boxes in this figure. Then these lists are used by the following force computation routines. In this figure, neighbor list generation shows the iterations that use the same neighbor list to compute forces. But there is also some communication overhead. Processes communicate the position of particles in ghost zones by neighboring processes. These operations shown here by green C boxes. Since particles move, we need to frequently move particles to their new processes. This operation is shown by green EX boxes, and we also need to update the border lists which are used to store the position of particles in ghost zones. And this operation is shown by UV green boxes in this figure. We propose to overlap the first force computation routine in the neighbor list generation with the neighbor build as shown in this slide. But as mentioned before, the highlighted force computation in this figure uses the neighbor list generated in neighbor build routine. So how we can run these two dependent routines, that means force computation and neighbor build, in parallel? The trick is the force computation uses the old neighbor lists from the previous generation. So it is important to note that this is not an exact copy of original MiniMD heuristic. We can consider our approach an alternative heuristic, a heuristic that exposes more task-level concurrency. We call this new heuristic the off-pass algorithm. The exchange routine, shown here with green EX boxes, changes the order of particles in the data structures that is used to store particles data. To merge the output of the force computation and neighbor build routine that run in parallel, we need to do the same reordering on the output of the force computation. We run the force computation on blue field in parallel with neighbor build, which is run on the host. The neighbor build is more compute heavy compared to the force compute, and since the host CPU is faster than blue field CPU, it makes sense to run force compute on blue field and the neighbor build on the host. Now let's see what happens with this benchmark on a real system. The one we use has 16 nodes. Each node has a dual socket Intel Broadwell and a Bluefield 2 from NVIDIA. First, we perform multi-node runs. On each node, we limit concurrency to only one MPI process running on the host and one running on the Bluefield, with no other threads of concurrency. In this plot, the x-axis is the number of particles, and the y-axis is the relative time improvement. Here the baseline is unmodified MiniMD, which is running on host nodes with conventional NICs, or network interface cards. Each color indicates a different reneighboring interval. It turns out this algorithmic change and code restructuring does yield a performance improvement. We observe a small but largely uniform speed up of up to 20% compared to host-only execution with conventional network interface card with the same number of nodes. However, we should compare this improvement against the power increase that we estimated to be as little as 6%. Another observation is that as the reneighboring frequency increases, the relative performance improvement increases. This is because the computation overlap between the host and the Bluefield increases for higher reneighboring frequencies. Our algorithm works best when it can completely hide the force computation time on Bluefield by overlapping it with the neighbor build on the host. This overlap depends on the relative computational power of the host and Bluefield. To study this scenario, we perform multi-node runs with one MPI process per host and one per Bluefield, with varying number of cores per host and per Bluefield. This is done using OpenMP with varying number of threads. In this plot, the x-axis is the number of threads on the host, and the y-axis is the execution runtime in seconds. Each color indicates a different number of threads on Bluefield. The teal line is in the plot shows the results for the unmodified MiniMD, which is run only on host nodes. By increasing the number of OpenMP threads on the host, the off-pass algorithm's runtime decreases and then stays constant. The knee of each curve indicates where the running times of neighbor build on the host and force compute on the Bluefield are closest. On each curve, for the data points on the left side of the knee point, the neighbor build on the host is slower than the force compute on blue field. But for the data points on the right side of the knee point, the blue field is the bottleneck. The knee point indicates the maximum number of OpenMP threads on the host where running force computation on blue field does not slow down the computation. Thread synchronization overhead in the force computation routine causes the performance not to scale proportionally to the number of threads. In this figure, we can see when increasing the number of OpenMP threads 8-fold, the off-pass algorithm speeds up by 2.5 times. This is because of synchronization overhead in the force computation routine. To better understand the performance of our offloading algorithm, we developed a simple performance model that estimates the runtime of the off-pass algorithm. We run the original MiniMD algorithm on host-only setting, and we measure the required time to complete each routine. As we can see here, we divide the total runtime of the algorithm to two parts. In this figure, one part is indicated with orange lines and the other part is indicated with gray line. One part is the time spent on the neighboring step. As we explained before, we changed this part in our off-pass algorithm. And then there is the rest which stays the same in off-pass and original MiniMD algorithms. Here we denote this part with T remain. The time spent on the neighboring step consists of a single force compute routine denoted by T sub fc and the neighboring routines denoted here with T sub n. Also, we run unmodified MiniMD in blue field only setting and measure the time spent on the routines shown in this slide. T sub ex is the time required to move particles to their new processes. T sub fc is the force computation time. And T sub c is the time required to communicate the position of particles in the ghost zones by neighboring processes. We use this measured value to estimate the runtime of the off-pass algorithm. Again, the predicted time denoted by T off-pass has two parts. One part is the time spent on the neighboring step. And then there is the rest that is the same as T remain measured before. The neighboring part in this case has synchronization barrier, so we have to take maximum of the time spent on the blue field and on the host. In this figure compares the estimated time for the off-pass algorithm, green lines, with the actual measurements, orange lines. In this plot, the x-axis is the number of OpenMP threads on host and the y-axis is the time in second. We show the result for two configurations. One configuration uses 4 cores on blue field and the other uses 8 cores on blue field. As shown in this figure, the model can closely predict the algorithm runtime. Let's now apply the model to analyze an alternative DPU design. The figure on the left depicts the actual system, where a node is a host processor coupled to a BlueField 2. The BlueField 2 has 8 cores and a modest peak of 80 gigaflops per second in single precision. The figure on the right shows a hypothetical system. We refer to the hypothetical DPU as an auxiliary node. In this design, suppose we replace the 8-core ARM in BlueField with a single core of the x86 host processor. That single core has a peak of 40 gigaflops per second. At first glance, this configuration seems worse than the actual system in terms of peak performance. The actual system has a peak of 80 gigaflops per second in single precision, and the hypothetical system has a peak of 40 gigaflops per second in single precision. But in fact, our model suggests this hypothetical system could attain the same performance, as shown in this plot. The dashed line is the hypothetical system, and this is because a single core on the auxiliary node avoids synchronization overhead. For a second hypothetical scenario, suppose we start with a single host CPU. It has a peak performance of 657 gigaflops per second in single precision. And it has a peak memory bandwidth of 76.8 gigabytes per second. Now suppose we consider the BlueField 2 network interface card with no host. It has a comparatively weak processor and low memory bandwidth compared to its usual host. Its peak performance is 80 gigaflops per second in single precision, and its memory bandwidth is 25.6 gigabytes per second. But if we put 8 BlueFields together, we can approximately match the host on aggregate peak, as you can see in this figure. Moreover, the aggregate bandwidth is much larger. (204 gigabytes per second versus 76.8 gigabytes per second. So what happens when we run MiniMD with full parallelism on the two configurations? The BlueField 2 configuration is 1.7 times faster. This is a real measurement, not a modeled one. Why does that happen? The building blocks are different. The flop-byte ratio of the comparatively weak blue field to processors is lower, making it a better fit to a computation that benefits from distributed communication. In conclusion, in order to get the maximum performance, we not only need to rethink algorithms, but also the configuration of the system. Here is other highlights from our work. We conducted performance analysis using the OSU Micro Benchmark suite and off-the-shelf version of MiniMD to understand the opportunities and limitations presented by the blue field for potential HPC applications. We also verified that the computed simulation result for the restructured method are still within an acceptable level of accuracy in terms of calculated physical quantities. For more details, please refer to our paper. The main conclusion is that off-path execution for HPC-type applications is feasible at a modest cost in terms of system power. The catch is that we will need to rethink algorithms and configurations. Looking forward, there is a lot of new work to be done. These include new applications, new algorithmic techniques, new programming models and runtime systems, and performance models to help us decide when and how to use the general purpose processing capabilities of DPUs. With that, I thank you for your time and attention.